into some microelectronics.
Let's do it.
Awesome. We've got some excerpts here from Sidra Microelectronic Circuits 7th edition.
Ooh, yeah, a classic textbook.
Yeah, it's kind of the go-to for this stuff. And our mission today, to really grasp those microelectronic circuits.
The fundamentals.
Exactly, fundamentals. How do amplifiers work? What's the deal with analog and digital signals? All that good stuff.
Sounds like a plan.
All right, so let's kick things off with signals. What exactly is a signal in the world of electronics?
Well, you can think of a signal as information writing on a waveform.
Okay.
It's the shape of that wave.
Uh-huh.
The peaks and valleys that carry the message, whether it's your favorite music blasting through your headphones
Right.
or, the data screaming a video.
I like that. So the wave is like doing a little dance and the moves are the information.
That's a great way to picture it. And to represent these signal sources, we use these concepts called Thevenin and Norton equivalent.
Okay, yeah, I vaguely remember those from circuits class. Long time ago. How do those work again?
So imagine a garden hose, right? With water flowing through it.
Got it.
The water pressure.
Yeah.
That's like your Thevenin voltage. It's the potential energy of the source.
Okay.
The flow rate of the water, that's like the Norton current.
Uh-huh.
It represents the actual flow of charge.
Got it.
Both describe the same source, just
Wow.
from different angles.
Interesting.
Yeah.
So it's like two sides of the same coin. One's the potential, the other's the actual flow.
Exactly.
Yeah. Now, in the textbook, example 1.1, it talks about source resistance impacting signal strength. Why is that?
Think about that garden hose again.
Okay.
You've got a kink in it.
Yeah.
What happens? The water flow, it's reduced.
Right. That's water combat.
That kink, that's like source resistance. It's hindering the flow of that signal so it loses strength.
So it's getting weaker before it even gets where it needs to go.
Exactly. And ideally, we want that source resistance as low as possible.
Okay.
So the signal stays strong.
Gotcha. So no kinks in our electronic hoses. Exactly.
Now, you mentioned earlier that electronics speak two languages, analog and digital.
Yeah.
What's the difference between the two?
That's a key distinction. Analog signals. They're like a dimmer switch.
Okay.
They can take on any value within a range. Think of a sunrise.
Okay.
The sky's color changes gradually, right?
Yeah.
From darkness to light.
Yeah.
Smoothly.
Right.
That's an analog signal. A digital signal. It's like a light switch.
Yeah.
It's either on or off,
Yeah.
1 or 0. No in between.
So digital is like steps, and analog is a smooth flow.
Precisely.
But why do we see digital everywhere now? Everything seems to be going digital.
You're right, and there's a good reason for that. Digital signals are much tougher.
Okay.
They're more robust to noise and interference. Think about a long-distance phone call.
Right.
An analog signal traveling over wires picks up all sorts of noise along the way, right?
Yeah, think so.
So the voice on the other end, it can sound distorted.
Yeah. A digital signal is less susceptible to that. It's easier to clean up a digital signal because you just need to figure out, is it a 1 or a 0?
Right.
Even if it gets a little fuzzy, you can usually tell.
So it's kind of like sending a message in Morse code. Even if some of the dots and dashes get messed up,
Yeah.
you can still probably figure it out.
Exactly.
Very cool. And digital signals are also easier to store, right?
Absolutely. Easier to process. That's why we use them for everything.
Computers.
Computers, smartphones, the internet.
Got it. Now, to bridge the gap between these two worlds, we've got these things called ADCs and DACs.
Great.
Analog to digital and digital to analog converters.
Precisely. They're like the translators between these two languages.
Yeah.
The ADC takes that smooth analog signal, converts it into ones and zeros that a digital system can understand.
Right.
The DAE does the reverse,
Back to analog.
takes the digital bits and converts them back to that smooth analog signal.
It's like translating a beautiful painting into a digital image you can share online.
Perfect analogy. So now let's talk about those devices that make these signals stronger. Amplifiers.
Amplifiers.
Hmm.
What do you think of when you hear that word? I think of a sound system at a rock concert,
Yeah.
making the music loud enough to fill the stadium. But I'm guessing it's a little more complicated than that.
You're right. It's more nuanced than just making things louder. Amplifiers, they don't just boost the signal's power blindly, they do it carefully.
Okay.
They make sure the quality is maintained. It's like a megaphone.
Okay.
A good megaphone doesn't just make a voice louder, it makes it clearer too.
Right. So it's amplifying without distorting keeping the message intact.
Exactly. And we've got different kinds of amplifiers depending on which frequencies they're amplifying,
Oh,
like low-pass filters.
Yep.
They only let the low frequencies through high-pass filters. They do the opposite.
Uh-huh.
And then you've got band-pass filters, which let through a specific band of frequencies.
So it's like specialized tools for different frequency ranges.
Mm-hmm.
Honestly, though, when I look at those complex circuit diagrams, I get a little lost.
Sure.
All those resistors, capacitors, transistors.
Uh-huh.
It's a bit overwhelming.
That's where simplified models come in. We don't always need to grasp every little detail.
Right.
We can use models that capture the essence of how the circuit behaves.
So instead of memorizing every single street in a city, we can use a map.
Exactly. And one of the most useful building blocks is the operational amplifier, or op-amp.
Ooh, op-amp. The name sounds powerful.
It is. In an ideal world, an op-amp has infinite gain, infinite input resistance, and zero output resistance.
Infinite gain. That's mind-blowing.
I know, right?
But I know real op-amps don't actually have infinite anything.
Huh.
What are their limits?
That's a great question. Real-world op-amps, while incredibly useful,
Yeah.
they do have limitations. One big one is something called slew rate.
Slew rate. What's that?
So an op-amp's output voltage, it can only change so fast. Slew rate is the maximum rate that output voltage can swing up or down.
Okay.
If the input signal changes too quickly,
Yeah.
the op-amp's output might not keep up,
Oh.
and you get distortion.
So it's like a speed limit for how fast the op-amp can react.
Precisely. And that slew rate limitation, it's something engineers always have to keep in mind.
Makes sense.
It's one of those real-world constraints that make electronics design both tricky and fascinating.
Absolutely.
You know, it's amazing how even with those limitations, op-amps are like the heart of so many circuits.
That's pretty impressive.
Really shows how clever those engineers are.
Totally. But speaking of limitations, we were talking about slew rate,
Right?
that speed limit for op-amps.
Mm.
Are there other things that affect how well an amplifier works?
Oh, definitely. Frequency response is a big one.
Okay.
Amplifiers, they don't treat all frequencies equally.
Interesting. So some amplifiers are better at amplifying certain frequencies than others?
Exactly. It's like our ears.
Haha.
We're more sensitive to certain frequencies.
Right. Amplifiers have their own preferences too.
So like some are tuned for bass notes and others are better for high-pitched sounds.
That's a great way to think about it. And one of the things that limits high-frequency performance is those tiny little capacitances we've talked about.
Oh, right, right.
Remember how they act like short circuits at certain frequencies?
Yeah.
Well, as the frequency goes up, those capacitors don't behave so ideally.
So at high frequencies, those capacitors start to mess with the amplifier's gain.
Exactly. Their impedance goes down,
Mhm.
and that can cause a drop in gain. It's like they're putting up a hurdle for the high-frequency part of the signal.
I see, I see. Now, the textbook mentions this thing called the Miller effect, especially when talking about common source and common emitter amplifier.
Oh, yes.
What is that?
The Miller effect, it's a bit of a mixed bag in amplifier design. Imagine a tiny balloon, right?
Okay.
That's your small capacitance.
Got it.
And it's connected between the input and output of a pump, which is our amplifier.
The Miller effect. It's like someone coming along and blowing up that balloon.
It just gets bigger.
Way bigger, making it much harder for the pump to work.
So a small capacitance becomes a big problem.
Yeah, because it increases the capacitance
Right.
and makes it harder for the amplifier to work.
So how do engineers get around that?
Well, they've come up with some clever tricks. One technique is called cascoding.
Cascoding, what's that?
It's like teamwork. Two transistors working together. In a cascode configuration, the first transistor does the hard work, the amplification.
Mm-hmm.
The second transistor acts like a shield, minimizing the impact of that inflated Miller capacitance.
Oh, so it's like a bodyguard for the first transistor, protecting it from the Miller effect.
Uh-huh, I like that. And this teamwork, it helps extend the amplifier's high-frequency response.
So it can handle those faster, higher-pitched signals.
Exactly.
Okay, all this high-frequency talk is making my head spin.
Right.
What about the low end of the spectrum? Do amplifiers have issues at low frequencies too?
They do. And in those discrete circuit amplifiers, the ones built with individual components, those large coupling and bypass capacitors are really important.
Oh, you mean those capacitors that we said were like perfect short circuits at those mid-range frequencies?
Exactly. But as the frequency gets lower, their impedance starts to increase. It's like they're starting to block those low-frequency signals.
Yeah. So it's the same as high frequencies. We get a drop in gain at low frequencies too.
You got it. And that's why choosing the right coupling and bypass capacitors is so important.
Yeah.
They need to be large enough to provide a low impedance path, even at the lowest frequency we need.
Sensing a theme here. Picking the right components is essential.
Absolutely. It's a balancing act. Larger capacitors are good for low-frequency response, but they take up more space on the circuit board.
So it's a trade-off between performance and practicality.
Exact.
Got it. Now, we've talked a lot about common source and common emitter amplifiers.
Right.
Are there other types, and do they have their own frequency quirks?
There's a whole family of amplifier configurations, each with its own strengths and weaknesses.
Like what?
Well, common gate amplifiers are known for their great high-frequency performance.
Oh, why is that?
Remember the Miller effect. Common gate amplifiers have a much smaller capacitance between the input and output.
Okay.
So the Miller effect isn't as much of a problem.
Got it.
They can handle high frequencies easily.
So they're like the athletes of the amplifier world.
Yeah.
What about common base amplifiers? What's special about them?
They have their own special skill.
Okay.
They have really low input impedance,
Hmm.
which is useful in some situations.
So it sounds like there's a whole variety of amplifier configurations.
You got it. It's like we have a whole toolbox of circuits, and we can pick the best one for the job.
That's pretty cool. This deep dive into amplifiers has been amazing.
It has.
We've covered so much, from how they work to their frequency response and all those cool configurations.
We have.
But our journey through the world of microelectronics isn't over yet.
Not even close.
We've still got more to explore. Okay, we've explored signals and amplifiers, but how does it all come together? Let's talk integrated circuits.
Ah, ICs. They're like miniature cities on a silicon chip.
That's what I always picture.
Yeah.
Tiny skyscrapers and intricate networks, all packed into something smaller than my fingernail.
You're not far off. ICs are incredible. They contain thousands, millions even, of transistors, diodes, resistors, capacitors, all connected together to do complex stuff.
It's mind-boggling how they fit so much into such a small space. How do they even design these things?
It's thanks to some amazing advances in semiconductor technology and fabrication processes. One of the big challenges in IC design is minimizing the chip area. That silicon real estate is precious.
So it's like designing a city where space is at a premium.
Exactly. You won't see big resistors or capacitors in ICs. They take up too much space. Engineers have to find creative ways to get the same functionality with smaller components.
So how do they do that?
One technique is using current sources and current mirrors. Think of them as the power grid of our silicon city. They provide stable currents to different parts of the circuit.
Like the electrical utility company, making sure everyone gets power.
That's a great way to put it. Current mirrors are especially clever. You can copy a reference current and use it in multiple places. It makes sure different parts of the chip perform consistently.
Like a blueprint, guaranteeing every building gets the same voltage and current.
Precisely. And these current sources and mirrors, they're essential for biasing those transistors we talked about, making sure they operate reliably in the right spot.
Ah, it all connects. Now, how do these IC amplifiers compare to the ones built with individual components, those discrete ones?
Good question. IC amplifiers have some trade-offs. One difference is their intrinsic gain. The gain without any feedback. It's usually lower than discrete transistors.
Why is that?
It's because of limitations in how ICs are made. The transistors in ICs are smaller, and their characteristics are a bit different from the larger discrete ones. For example, the early voltage is typically lower in IC transistors.
Okay.
But engineers have figured out how to work around this. Remember feedback? It's not just for reducing distortion, it can boost gain too.
So we can still get high performance, even with lower intrinsic gain.
Exactly. Feedback is super important in IC amplifier design.
Now, those op-amps we talked about earlier, those
Yeah.
are integrated circuits too, right?
Absolutely. Op-amps are a classic example of how IC technology lets us create really versatile building blocks. A single op-amp chip can have dozens of transistors, all connected to give those ideal characteristics. High gain, high input resistance, low output resistance. It's amazing how small they can be.
It is. And op-amps are the basis for tons of analog circuits, right?
Right. Filters, oscillators, amplifiers, they really show the power of integration.
We started with signals and components, and now we see how it all comes together in integrated circuits.
It's quite a journey, isn't it? And this field is always changing. New materials, new fabrication techniques, new designs. The possibilities are pretty exciting.
So those silicon cities are just going to get more complex.
Absolutely. And as we depend more and more on electronics, it becomes even more important to understand these fundamental concepts. It helps us appreciate just how much ingenuity goes into these tiny but powerful devices.
Well, I think we've given our listeners a good starting point to explore this world further. It's clear that microelectronics is about more than just circuits. It's about human creativity and innovation.
Couldn't agree more. Who knows what amazing discoveries are still to come? It's a great time to be following microelectronics.
That's a perfect note to end on. Thanks for joining us on this deep dive into microelectronics. Until next time.